So we're going to continue to work on the binomial distribution. And again, let's remind ourselves, because we had an exam, we kind of forgot some things. So binomial means there's only two outcomes. We generally label the outcomes success and failure. Now that does not mean you succeeded or failed. A success or a failure is whatever it is you're counting. If that thing occurs, we call it a success. If it doesn't occur, we call it a failure, because you're counting only one of the two outcomes. So if it's a heads or a tails, and I'm counting heads, then heads are a success and tails are a fail. If I'm rolling a single die and I'm counting sixes, then sixes are a success and everything else is a fail. That's all that means. A lot of people read more into it than that. So n is known. Why is that important? Because there's two kinds of experiments you can do with binomial. You see, I can say, I want you to flip a coin until you get 10 heads. Could you reach it in 10 flips? Is that possible? Could it be 11? Could it be 20? Could it be 30? Does any human being know how many it's going to take? No. So n isn't known. If I said do something until you reach a certain goal, then there's no way you could know how many trials. That's not a binomial experiment. That's something else. No, the binomial says I want you to flip the coin 10 times, and now I want you to count the outcomes. Okay? So binomial experiment, n is known, p and q are fixed. And what I mean by that is they don't change. The probability of a heads doesn't change because of the last flip. Right? So, firstly, you flipped the tails. Oh, now the probability of heads is going to completely change on the next one, isn't it? Because the dice is, or the coin is keeping track. It's got a little computer chip that's counting, right? That's how it works. When you roll the dice, it's counting, or no. When you shoot that free throw, make or miss, the ball doesn't remember whether it went through or not, does it? So the next time you shoot the free throw, your probability of success is exactly the same as what it was a moment ago. Right? Things like that don't change, and that's really important. So the probability of success and fail don't change. Are there things that we've done where it does change? Yes. Pick a card, any card. Look at that card, either set it down or put it back in the deck. If I put it back in the deck and reshuffle, then probabilities stay the same, don't they? But if I set the card down, now I have a different amount of cards in my hand. You're pulling the red and the blue marbles out of the bag. You look at your marble. Are you putting it back in the bag or are you setting it aside? In other words, the with replacement versus without replacement can change these. So that would not be a binomial experiment if I do not replace it. But if there's only two colored marbles and I'm always putting it back in, then that becomes a binomial experiment because the probability of success will stay the same forever and ever. Now tell me about P and Q. What must be true? What must they add up to?
1.
1. Right? The probability of success plus the probability of failure is 1 because there's nothing else. So usually we think about it, I know the probability of success, therefore I just go 1 minus that. So if it's a coin flip, it's really easy. They're both a half. But if it's the roll of a single die, it's 1/6, 5/6. Right? If I'm pulling a card out of a deck of cards, my denominator is probably 52. Okay? So there's every problem's a little different. We're going to look at several of them today. And then, if this is the case, if the random variable x is the number of successes, then x can be anything from 0 all the way up to what? N. Is it possible, whatever you're measuring, that you are successful on every trial? We're going to do some Kobe Bryant free throws later. Is it possible Kobe made all of his free throws? Sure. Is it possible he missed all of his free throws? Yes, probably a lot less likely, but these things are all possible. So everything from nothing to everything, and then we know then the formula, the probability of x is n choose x, because there are n trials, there are x successes. P and Q, P is always raised to the number of successes, Q is raised to the number of fails. Well, if I succeed x times, then I must fail n minus x times, because those two numbers have to add up to the number of trials. This is the formula. It's actually very simple if I have a cheap calculator. If I've got a complicated, fancy calculator where I've got to go through menu options, this can be a little more of a challenge. That's why I say in a class like this, you don't want a fancy calculator. You want something that's really, really easy to navigate and manipulate. I'm giving a linear algebra exam tomorrow, and they can use calculators, but the most they're ever going to do in that class really is basically adding fractions of different denominators because they're doing matrix algebra. That's literally the only thing they need a calculator for. And so I had people ask me, can I use a graphing calculator? I said, sure, but graphing calculators tend not to have fraction keys. So every time you want to add a fraction, you've got to go through an entire series of menu options. It's like, no, grab a cheap calculator where the fraction key is a main key, then you can get through that in a few seconds. If you have a fancy calculator where you've got to dig deep just to do one calculation, that's not to your advantage. See, I teach calculus and above primarily, and graphing calculators are awesome for graphing. They're almost worthless for anything other than graphing because they're too hard to use. It takes too long. You want to add two numbers, you got to go through a series of menu options, select math option, plus sign, you know. It should always be simple and easy to do a calculation. But if your calculator is not user-friendly, you know, that's the thing. So here's what we're going to start with. We're going to flip a coin 8 times. We want to count the number of tails. And then we're going to make a probability distribution. Now, I love starting with coin flips because P and Q are both a half, and all of the calculations as a result tend to be really, really fast and simple. We're going to do other things where it's not a half, but we're going to start with this. Now, what we want to do is we want to make a probability distribution. That's where we put all the possible outcomes, the probability of every outcome. We'll consider what does a histogram look like just so we can see a visual of that. But we also then want to find the expected value, we want to find the variance, and we want to use the range rule of thumb to determine what is a reasonable set of outcomes. These are the things that we do with binomial distributions in general, and we're going to do all of them for several different problems today. And hopefully by the end of the day, you guys can go really fast through this. But this original problem is not going to be fast because we've got to do 9 calculations. 8 coin flips, right? My outcomes are everything from 0 to 8. So we're going to let x, the random variable x, be the number of tails. Then x will equal anything from 0, 1, 2, 3, 4, 5, 6, 7, or 8. So we've got to calculate each of those probabilities. But what we're going to find is all of them are going to have the same denominator. Does anybody want to venture a try at what the denominator is going to be for every one of these?
256.
And how did you come up with that, Dylan?
There's 8, 2 to the 8th power.
2 to the 8th power, right? 2 times 2 times 2, because I have 2 choices for each outcome. So there's going to be, we're not going to do this, but if I wrote the sequence of 8 heads and tails, by the way, I'm using 8 particularly. Are there any computer programmers in here? Anybody's ever written code of any kind? Even in high school? What is a bit? It's the sequence of zeros and ones. And exactly how many zeros and ones are there in that sequence? 8. 8. So how many different bytes are there? 256. All computer language uses the exact same starting point. There are 256 different symbols, in other words. The sequence of zeros and ones each means something, and there's exactly 256. How do I know? Because there's 8 positions, and each one's either a 0 or a 1. I have 8 positions, each one's either a H or a T. It's exactly the same thing. So there's 256 outcomes if I actually wanted to do it. H, 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 T. I don't want to do that. It takes way too long. So we use this to do our calculations. Well, I erased it. So if you know that it's going to be 256, that's because of the 1/2 raised to powers. Then the probability, we're going to do each one. The probability that x equals 0, we can just write it like this. This is the formal textbook notation. I mean, there's no way we can get confused. We're counting the number of tails, so we can just say probability of 0. What is it going to be? It's going to be 8, choose 0. Let's remind ourselves, because we've said it out loud, but I'll rewrite it up here. I know that n is 8. P and Q are both 1/2. It's a coin flip. Okay? So it's going to be 8 choose 0, 1/2 to the 0th power, 1/2 to the 8th power. Again, 8 trials, 0 successes, 0 successes, 8 fails. But isn't this still just 1/2 to the 8th power when I put those two together? What is 8 choose 0? How many ways can I select 0 things? One way. So this is 1 over 256. I want to leave these in fractional form. This is actually easier to deal with. We don't always do that. We often leave it in decimal form because it's too big. But this is small enough that we can still do this. So the probability of exactly 1. Okay, well, there's 8 positions I can put that tail in. So it's 8 choose 1, which is 8, by the way. 1/2 to 1 success, 1/2 to 7 fails, and that's going to be 8 over 256. Yes, I can reduce that. I don't want to reduce these. In all of your life, you're told you always reduce fractions. In a final answer, that's a good thing. But we're going to do these for every one of them, and if every one of them has the same denominator, I really don't want to reduce any as I go. It's harder to work with multiple fractions if every one of them has a different denominator. Do you agree with that? So I actually want to leave the denominators the same. In a final answer, we can reduce a fraction. But if every one of them is going to have the same denominator, let's take advantage of that. Okay? I'll put P2 here. I'm going to need lots of room. So now I have 2 successes. Okay? There's 28 ways to do that, by the way. 1/2 to the 2nd power, 1/2 to the 6th power. And that's still, that's still going to give me this. So what does this turn out to be? It's 28 over 256. All right, let's keep going. Probability of exactly 3. So that's 8 choose 3. 1/2 to the 3rd, 1/2 to the 5th. Now I'm going to erase the instruction here because we all know what it is. Now what does this turn out to be? What's 8 choose 3?
56.
56. So this is going to be 56 over 256. Excellent. P4. 8 choose 4. See, we can be thoroughly lazy in terms of the calculation. Because it's 1/2 to a power, every one of these has a 1/2 to the 8th, ultimately, doesn't it? So there's my 256 in the denominator, so the only calculation I really have to do is the combination. So what is this one?
70.
70?
Yeah.
Okay. Now you should notice something about right now in the problem. $56. Wait, why was it why were these the same? To get 3 tails and 5 heads should be the same as getting 5 tails and 3 heads. I have 8 people in the room and I want to take 5 of you to lunch. Isn't that the same as deciding which 3 to leave behind? And that's why it's the same thing. We know that it works that way. So that makes the rest of the calculations actually quite simple in this case. By the way, it's only because P and Q are a half. That's not always true. Not all, only in this case here. All right, so let's keep going. And this one should be, what, 28 over 256? And this one should be 8 over 256. Because I need to, of the 8 slots, I got to put tails in 7 of them. Isn't that equivalent to saying which one slot do I want to put the heads in? It's the same thing, isn't it? Sometimes it's easier to think about it in those terms. And then finally, the probability of getting all 8 tails. We know there's only one way to do that. So that one should be 1 over. Now, at this point, tell me what everybody should be doing with those probabilities before you move on to the next step.
Add them.
Add them and make sure of what?
One.
They add to 1. If they don't add to 1, what does that mean?
I don't know.
That means somewhere I have an incorrect calculation. Is that possible that we get an incorrect, that you hit a wrong button on a calculator? Yeah. I mean, unless these were so easy you could do all of them in your head, it's very possible that one of these numbers is incorrect. So add them all up real quickly. By the way, don't add up the denominators, just add the numerators. So 37, and down to 93, and 163, and then 249, right? Where are we right now? So just look at so. It was like 219, 247, 255, 256, yeah. So they add up. Now let's make our probability distribution. What is the biggest number? I flipped a coin 8 times. What outcome has the highest probability? 4. Does that surprise you, or is that exactly what makes sense? Now, is it overwhelmingly? No, 70 over 256 is not a very big number, right? It's only a little more than a quarter, but it's higher than any other outcome. And by the way, what are the next 2 highest outcomes? 3 and 5. Oh, that kind of makes some sense. So if the highest outcome is 70 over 256, if it helps, we can, what is that as a decimal? It's about 0.27. You could do this in decimal terms, or you could just do it in fractional terms. So maybe I go like this. 10, 20, 30, 40, 50, 60, 70. I'm going to be really lazy. Right? So that'll be 20 over 256, and that'll be 40 over 256, and that'll be 60 over 256. Then I have 0, 1, 2, 3, 4, 5, 6, 7, 8. Sometimes the visual is really useful. It doesn't help me do the calculations. I've already done the calculations. So 0 is only 1. So 20, 10, this is like barely registering. This guy's barely registering. I mean, it's almost a line. But then next one's up to 8, so that's almost all the way up here. And so is this one. And then the next one is 28. So that was 10, 28, so it's way up here now. And then the next one was 56, 10, 20, 30, 40, 50, so we're about here. And then the last one being 70 is all the way up to here. Now, if you do this on graph paper, it's obviously a little easier because you got the lines. Now, do you notice something about the shape of this thing? It's perfectly symmetric, isn't it? Now, here's what I want you to think about, because this is where we're going in the near future. These are rectangles. And you're always going to have this symmetry. This is because it's a coin flip. True-false test. 1s and 0s. When there's only 2 outcomes and they're equally likely, you're going to get this. And I mentioned this to Dylan last time. What if instead of 8, I had 80, but I wanted to still fit it on this picture? Then all of these rectangles would be really skinny, wouldn't they? What if I wanted 800 and I wanted this much room? They're literally going to look like line segments, aren't they? Is everybody with me so far? What is the shape of this start looking like? Does anybody know? The shape starts looking, curvy. And in fact, it starts forming that nebulous bell-shaped curve that some of you have heard about. There's a lot of things people refer to as a bell-shaped curve. There's actually only one of them mathematically, and we are actually going to introduce it next class. But that's what the binomial will start looking like. It'll start looking like that bell-shaped curve. That has a really important name and a really, it's calculated a certain way. But it's kind of interesting that the more times I do this, the more this looks like the curve, even though they're little rectangles. Those of you, if you remember your high school geometry, you had a regular triangle, equilateral triangle. You have a square. Maybe you have a regular octagon. Regular means all the sides are congruent, all the angles are congruent. But I keep putting more sides. Now I have 20 sides, I have 50 sides, I have 100 sides. What's happening? All my sides are getting shorter and shorter. And what is the shape starting to look like after a while to the naked eye?
Circle.
It's starting to look like a circle. Well, it turns out if I look at the area and perimeter of this polygon, the more sides I have, the closer it becomes to the area and perimeter of a circle. It's kind of cool. So if I had a computer generate a 1,000-sided image, the naked eye, it would look like a perfect circle. You couldn't see the difference because the sides would be so short. And this is kind of the same idea. In calculus, we call this a limit. It's a very, very huge concept that they get closer and closer and closer and closer. And we say they converge. That's what's happening here. It gets closer and closer and closer to the bell shape. And then I can use certain properties from one to the other to make it easier to do calculations. Okay, so we got all this. Now that we have all these numbers, I want to calculate the mean. I want to do this so you can see, but let's do this over here. So the mean, which is called the expected value, and I want to do the variance. Okay? So what does that mean? Simple terms. That means 0 times this plus, 1 times this plus, 2 times this, all the way to the end. Okay? So on our calculators, let's do this. I did not set up the table like I usually do for the distribution, because I got all the numbers up there. But what I mean by the table is this one here. Remember we've been doing this? 0, 1, 2, right? And we put the probabilities. We've got them all there. I don't need to create a separate table. So what I want you to do is take every one of the outcomes. So remember, it's the formula is x times probability of x. So it's 0 times its probability plus 1 times its probability, 2 times its probability, all the way up to 8 times its probability. Let's do that one first. Because the variance needs the outcome of this, remember, because the variance is minus the mean squared. So I actually have to do this one first. This is the calculation we're performing now. All the way to the end. Let me know when you get a number. By the way, you can be clever. Since every denominator is 256, can you just add up all the numerators and then put your answer over 256? See, that's what I do. I'm lazy. Since every one of these denominators is the same, just add up the numerators and then put your answer over 256. It's actually a lot faster to enter into your calculator. And by the way, when you're doing this, you do not need parentheses. When you do this times this divided by this, you don't need parentheses. Order of operations, your calculator is going to do the right thing. When we write it down, we often write it with parentheses. That's for readability. That's so nobody can get confused by what I'm saying. But you don't actually have to enter it with parentheses. Okay? Just to remind us. Anybody got a number yet? You got one? What do you got?
4.
4? Exactly? Exactly 4? So you're telling me if I flip a fair coin 8 times and I calculate the expected value of x, it's exactly 4? Wait a minute, doesn't that make perfect sense? That a coin, I should expect exactly half of them to be tails? By the way, you just did it by calculating. I didn't tell you that the answer was 4. You calculated the answer was 4. That's a big difference. So keep that in the back of your mind. We're going to do a few more examples and we're going to come back to this. Now let's do the variance. So the variance, remember, is this. Outcome squared all the way to the end of the line. And then what's the last one? Plus 8 squared times 1 over 256. And then minus, remember, minus that squared. This is the variance. So it's the exact same calculation as the mean, except that, remember, I'm squaring all the x's this time. Same probabilities. That's why when I write them down, I like to stack them. I always like putting one right over the other, because then I'm much more likely to do the numbers correctly. In reality, you're not going to do this problem with a ridiculously large set of numbers. You're going to do this with a fairly small. On your quiz, I think I had you do it with, what, 5? You know, maybe 5 or 6 things. It becomes impractical if it's too big. But we need to do it for the small so we know exactly what went into the calculation. Okay? So, does anybody have an answer for this one? Tell me when you get this one. should take just a tiny bit longer. Anybody got it? 2, exactly. That sounds about right. 2. Now, I'm not sure what to do with that number yet. That's the variance. What number do we actually use when we're figuring out the range rule of thumb? Do we use the variance or the standard deviation? We use standard deviation. So, but by the way, we always calculate the variance first. You know, on your exam, you calculate s squared, and then you take the square root of that answer for your standard deviation. But you always start by calculating the variance. So what is the standard deviation then? The square root of 2. That's what it is. Now I said we want to use the range rule of thumb. So we flipped a coin 8 times. We calculated that the mean, the expected value, is 4. That's like the oh duh. Oh, that's exactly what it should be. We didn't know about the variance. We calculated the variance as 2, so the standard deviation is the square root of 2. We're going to use our calculators in a moment. The range rule of thumb in simple English says the vast majority of all outcomes are within 2 standard deviations of the mean. We now know the mean and the standard deviation. So the range rule of thumb, I'm going to call it the RRT, how's that? I'm running out of space. Says that it's mu plus or minus 2 sigmas. So in this case, that would be 4 plus or minus 2 root 2. So on your calculator, let's calculate what these numbers would be, okay? So what's 4, and by the way, now you want to use a decimal. So 4 minus 2 root 2, it's about 1.17. And I'm going to say, range rule of thumb says our outcome should be in this range. And then 4 plus 2 root 2, about 6.83. So the range rule of thumb, now can you get 6.8 tails? No, it'd be okay to just say 7. So the range rule of thumb says what? I'm going to flip a coin 8 times. The vast majority of all my outcomes should be between 1 and 7. What am I excluding? 0 and 8. But those have probabilities of 1 over 256 each, don't they? So the outcomes that I'm including are 254 out of 256. That's so well over 99%, by the way. Does that make sense to you? That's what the range rule of thumb says. Oh, that if I flip the coin 8 times, the vast majority of all my outcomes should be between 1 and 7. And that makes perfect sense. Is it all outcomes? No. By the way, it can be. It usually isn't. It could be all outcomes. I said the vast majority. So that's kind of cool. Range rule of thumb says, hey, if I'm going to flip a coin 8 times, what term do we use for the 0 and 8? There's another term we use? Those are the extremes. We often call them what? Outliers. Yeah, they are very unlikely. Are they impossible? No, they're just not very likely. Now, if you flip the coin enough times, let's say you flipped the coin 1,000 times, you might get a sequence of 8 in a row. That wouldn't be unusual. Now, this is a classic statistics experiment, and I cannot quote you exactly where it came from, because I read about this even when I was in school. It was, I believe it was an Ivy League instructor. He's teaching a stats class, and I love this. I love this. He had people be on the honor system. And so he asked his students, he says, I want you all to flip a coin, and it was some really large number. It was like maybe 200 times or something like that. And I want you to write down the outcomes, tail, tail, head, head, that kind of thing. And he says, but if you don't want to, you can just make up the outcome. But he says, I will then tell you if you made it up or you actually flipped it. Now think about this logically. So you actually flipped it, you wrote them all down, you decided to make them up. And I could say, yeah, you did yours legit, you made yours up. And he, by the way, he was a huge class, like 300 people class, and he was absolutely correct on every single person. How is that possible? How did he know when they made it up? Because what do people naturally do if they were making it up? Tail, head, head, tail, tail, head, tail. Rarely would they even put 3 in a row. But because of the number of times he had him do this from a probability standpoint, it would have been extremely unlikely not to have sequences of at least 5 or 6 with that many flips. And the people who made it up never had sequences more than about 3 in a row. Because they just think naturally, oh, it's never going to be 5 or 6 in a row. Actually, the probability says if you do it enough times, you should have lots of long sequences. Isn't that crazy? So he was able to figure out who was cheating. By the way, they weren't in trouble. This was the whole idea of the experiment, that he could tell you if you made it up because of your lack of sequences. The people who made it up never really put more than 3 in a row. Occasionally, maybe they'll put 4 in a row, tails or heads. Not realizing the probability says, no, you should have longer sequences when you do it that many times. Isn't that crazy? That's kind of a cool thought. So if you're saying, well, you're never going to get 8 in a row, you did it enough times, you ought to get 8 in a row or more at some point. So this was a fairly simple notion. So I want in the back of your mind you to keep track of this, because now we're going to go to something else. This was the coin flip. Now we're going to do the multiple guess test. Okay? Now this one, unfortunately, is not going to be quite as simple. So, but I'm going to do fairly small numbers. So Dylan, you were with me, we did a problem like this the other day.
Yeah.
It's going to basically be the same problem because otherwise it's just too long. So, there's a 5-question, and I'm going to do 5 questions so you only have to do 6 calculations. Okay? A 5-question multiple guess. And I say multiple guess because you accidentally walked into the wrong room and you sat down and they handed you a multiple guess test in a different language. But you had to do it. So obviously you guessed on every answer. I'm making the assumption that you literally are guessing on every answer. You don't know any of the information. Okay? Let's say there are 5 responses to each question. Now this is important. The 5 responses to each question are important. If there were 5 responses to the first question, but only 4 to the second, and the third one was a true-false, this is not a binomial experiment. Why? Because the probability of success and failure would change on each problem. So that's why it's important that regardless of how many responses you have, it's always the same. I used 5 because then it makes our numbers a little bit easier to interpret. All right? So what we want to do, obviously we want to let x be the number of correct answers. Okay? You all agree with that? I don't want to keep track of the wrong answers. I want to keep track of the right answers. So x can be what values? 0, 1, 2, 3, 4, or 5. We want to calculate the probability of each of these. Now, this is not a coin flip anymore. Are you more likely to get an answer right or wrong? Wrong, because what is the probability? Let's write this down now. Excuse me. So in this experiment here now, n is 5, whoops, sorry, and p is what? 1/5, because you have 5 possibilities and only one of them are correct. So if p is 1/5, what's q? 4/5, that's it, because it's got to add to 1. This is not a coin flip. It will not look the same. There's no part of this problem that's going to look the same, including the histogram. And that's why I want to do this so that you get a visual. So let's do the same thing. We're going to go the probability of 0, the probability of 1, the probability of 2, 3, 4, 5, and 6, just like we did here. All right. Let's start with these guys now. So this will be 5 choose 0, but now instead of 1/2, it'll be 1/5, 4/5. 5 choose 1. I'll put the exponents in a moment. 4/5. 5 choose 2. 1/5, 4/5. Now remember, it's always p to the number of successes, so this would be to the 0. So this would be to the 5. I have 0 right answers, means I have 5 wrong answers. The next one, I have exactly one right answer, so that's a 1. So I have exactly 4 wrong answers. Because my exponents have to add up to 5, because I'm doing this 5 times. The next one, 5 choose 2, so it's 1/5 to the 2, 4/5 to the 3. We'll calculate these in just a moment. I just want to write them down first. Now, in this case here, you could write these as fractions. There would be nothing wrong writing these as fractions. The dilemma is your denominators would all be 3,125, which is absolutely correct. But it makes it a little bit trickier, so I suggest at this point, let's use decimals. Just because keeping track of the fractions now starts getting a little bit ickier, okay? Now, by the way, everything I wrote is correct. When I do 1/2 or 1/5 to a power, I go parentheses, 1 divided by 5 parentheses. Is there an easier way to do this? Instead of using 1/5 and 4/5,
0.2 and 0.8.
what if I use 0.2 and 0.8? Then I don't need parentheses. Instead of going parenthesis, let's keep counting. Parenthesis, 1 divided by 5, close parenthesis. No way around it. That's 5 keys, exponent. 0.2 exponent. Oh, 1 key. I can go for that option. Can I always do this? You can only do this if P and Q are terminating decimals. You cannot do this if you had to round. There would be no calculation that exists that you would get a correct final answer if you're rounding P and Q and then calculating them to high exponents. So if P was a third, just leave it as a third then. But because you can calculate these, 0.2 and 0.8 actually makes the calculation significantly faster. Okay, but I'm still writing down, but you enter it the other way. So then I have probability of 3, probability of 4, probability of 5. When it comes to calculations, I am lazy. I always want the easiest, fastest way out, but I still want to be right. Okay, so this would be 3 and 2, 4 and 1, 5 and 0. All right, now let's get the numbers. This should be relatively simple. And that's why I like the cheap calculator. Oh, one too many zeros on this one, sorry. There we go. That's good. Okay, so hopefully you guys are able to get those relatively fast. Yeah, cheap calculator, way faster. Now, add up your decimals, make sure they add to 1. There was no rounding here. All of these were terminating decimals. But by the way, I don't say that to be flippant. I say I would always do this. Okay, I trust my ability to get a calculator right. I'm going to be right probably 99% of the time. Which means I'm going to be wrong 1% of the time, and I don't know when that 1% is, so I always check. If this doesn't add to 1, I just a moment ago inadvertently had an extra 0 here. Those wouldn't have added to 1, would they? But I fixed it. But that wouldn't have worked, and I wouldn't have been able to figure it out. So we add them up, they add to 1, hopefully. Okay, let's make our picture. This one's gonna be very different than the other one. Everything about this problem is gonna feel different, but in the end, there's gonna be tremendous similarities between this and the coin flip. Okay, my highest probability number I see is just over 0.4, so I'm gonna put 0.4 here. You know, 0.2. A lot of us are not good at this part here. The scale should be the same. Whatever this is, it shouldn't be random. That's why graph paper is so effective. Binder paper is probably not as good. It's probably off here. Okay, so my outcomes were 0, 1, 2, 3, 4, 5. So the probability of getting 0 right is actually really high, isn't it? It's about here. I'm going to guess on all 5 questions. That's almost a third, isn't it? So everybody in here is going to do the same thing. You're all going to guess on all 5 questions. That says about a third of us are going to miss all 5 questions. Whoa, that's a lot, isn't it? But, again, my probability of success isn't very good. Now, what's the probability I get exactly 1 right? That's even higher. That's way up here. Between those 2 outcomes right there, I'm almost 3/4. Wow. So, again, all of us are guessing on every single question. That says about 3/4 of us are going to get either none right or only 1 right. That's an easy way to think of that. All right, the next one, 0.2, about right here. The next one is 0.05, I'm only about here. The next one, 0.006, I'm only about maybe here. And then the last one, I can't even see it. That's so small. What do you notice about this one? It is skewed. Remember that? This is like income and housing kind of thing. Oh, yeah, the probability, it goes down that way. Most of the outcomes are at the beginning. Now, does this make sense to you? The most likely outcome, the highest probability, was to get exactly 1 right. Second, none right. 2 right, and so on. To get all 5 right is mathematically possible. A very, very low probability. Okay? You with me so far? Now let's calculate the expected value and the variance. I'll put it up here. So the expected value, which of course, I'll remind us that is the mean, so that would be 0 times its probability. I'll just put it in front. 0.32768 plus 1 times its probability, all the way down. Now, take your time. There's not that many numbers, and we want to make sure we enter them correctly. We do not want any sort of calculator errors. Well, I shouldn't say calculator error, say calculation error. Your calculator is not going to make an error. I always love when people say, it's a calculator error, it's a computer error. No, actually, calculator gave you a perfect answer. It gave you exactly what you asked. You might have asked the wrong question, though, right? My fat thumbs, I don't say it jokingly, my fat thumbs, I hit wrong buttons all the time. You should see my texts. That's not what I typed. Right? It's not the phone's fault, it's my fat thumbs. So it's easy to hit the wrong button. That's why you got to check. All right, so let's do this all the way out, exactly 6 values, and then we're going to do the variance. I know it's a little bit tight up here. And then at some point it's minus, right? We have to calculate the mean first so we know where we're at. So tell me when you get a number.
I have 1.
Who got 1? You got 1? Exactly? With all those decimals? Seriously? Yeah, you got 1. I just guessed at 5 questions on a multiple guess test that had a 1/5 probability, and the calculation said I should expect to get exactly 1 correct. Again, doesn't that feel like the ODA answer? I have a 1/5 probability of being right, and I get exactly 1/5 of them right, is what the math says. The coin flip, I have a 1/2 probability of getting a tails, and the calculation says I should get 1/2 of them right. In other words, I should get 1/5 of all the questions right. Whether it was 5 or 5,000 questions, I should get 1/5. And by the way, that is exactly what the calculation will always produce. Isn't that crazy? Now, let's calculate the variance, because that one's a little bit busy also. I'm going to erase this graph because I don't need it anymore. Let's calculate the variance. It'll actually come out decent, by the way. But now it's -1 squared. That's why I was waiting. That is the only part of the problem that people tend to forget, is minus the mean squared. And they'll say, why is this not working? You have numbers?
0.8.
Exactly? Exactly 0.8. Yeah, that's correct. So once again, let's use the range rule of thumb on this. The range rule of thumb says, again, the vast majority of all outcomes will be within 2 standard deviations of the mean. Well, my mean in this case was 1, so I'm going to go 1 plus or minus what? 2 times the square root of 0.8. Okay, so let's do that on our calculator. 1 minus 2 times. From about negative 0.8, well, I can't get a negative number correct, but that's what I got, to about 2.8. Okay, that's what anybody else get that? Did I get that right? Wait, I don't like, something about that I don't like. Let me do that again. Hold on, 1 minus 2 times. Yeah, okay, negative 0.8. Oh, yeah. 1 point, yeah, it's about right. Okay, well, what's the worst you can do is 0 right. So really this is saying what? I'm going to be between 0 and what? 3. So it says, I'm going to go guess on every question on a 5-question multiple choice test, and everybody in this class is going to do the same thing. The vast majority of all outcomes should be between 0 and 3 correct answers. What are we excluding? We're excluding these 2, which add up to significantly less than 1%, by the way. In other words, we've covered over 99% of all. If I add up all the other ones, it's more than 0.99. Again, does that make sense to you? Think, oh yeah, that is kind of a common sense thing. The vast majority of all outcomes should be between 0 and 3 right answers. 4 right answers would be extremely unusual. 5, not impossible, but very unlikely, right? Okay, now, let me go back. Here's the second problem. Do you notice anything? Well, the obvious thing is, if the probability of success is constant, what, a half, a third, a tenth, doesn't matter, then I should get that many successes overall. Think about anything. You're an 80% free throw shooter. Shouldn't you make 80% of your free throws then? Actually, that's what the math says. So here's the big picture. Here's the big, humongous result, which is so cool because it's absolutely true. Now, there is a formal mathematical proof, but you kind of need a math degree to see it. I literally saw this in grad school in statistics. The formal math proof of what I'm going to tell you is your head would explode. But for a binomial experiment, with n, p, and q given, the expected value of x is simply np, always. And that's the ODA. The probability of success multiplied times the number of times I do it should be exactly how many successes I have. If the probability of success of whatever you're doing is 1/4, and you do it 100 times, then you should be successful 25 times. That's the ODA, and that's what the calculation will always produce. Isn't that cool? And the variance, you may not see it, it's right there. My expected value was 4. Huh. My expected value was 1. Do you see it? If I take my expected value and multiply it by Q, I got my variance. So my variance is simply NPQ. And this is considered one of the single most important results in all of statistics, and it is so easy to use. It is so easy to use. We had to do this to see it. I could have told you, but you wouldn't have seen it. You just did it and you saw it, didn't you? So now, there's an exam coming up, but it's 100 questions. And you have 5 responses to each question. And you didn't have time to prepare for that exam. How many can you expect to get right? 100 questions, 5 responses to each question. How many can you expect? 20. 1/5 of 100. And by the way, does that mean you're going to get 20? No, but imagine you're at UCSD and there's 300 people in the class and every single person forgot to prepare for the exam and they all guessed. It's basically saying that the average number of right answers among the entire group should be literally exactly 20. And law of large numbers says that it applies, that's what the law of large numbers applies to, binomial experiments, that what you see should be exactly what you expect to see. Now, this is where I have fun. You have a friend who took that 100 question test, and they said, oh yeah, I got 60 right answers. And you're like, wow. And they said, I guessed on every question. And I got 60 right answers. Are they telling the truth?
Possibly.
Possibly. Good. Do we have a way of determining it? Yes, we do. And I'm going to show you, this is kind of cool. They actually use this type of mathematics, by the way, in courts of law. Statisticians are brought in all the time to challenge claims that the common sense people say, oh yeah, it sounds good, and like, nope, mathematically it's virtually impossible. All right, you have a 100 question multiple guess test. P is this, Q is this. Okay, what is the expected value? That's my mean. It's 100 times 1/5, agreed? I expect to get 20 right. What's the variance? Sixteen. So therefore, what's the standard deviation? Oh, this came out kind of nice. Your friend claims they got 60 right answers. If the mean is 20, the difference from 20 to 60 is 40, agreed? If the standard deviation is 4, that means that's 10 standard deviations exactly. The probability of being 10 standard deviations would be basically a decimal point with 1,000 zeros. You're more likely to be struck by lightning 25 times in the next 8 seconds, in other words. Is your friend telling the truth? No. It's not that it's not possible, it's that if somebody did this, they guessed it 100 questions, 1 billion times, 1 trillion times, it still probably wouldn't happen that they got 60 right. The probability is so small because all I have to do is look at how many standard deviations. In most scenarios, it's virtually impossible to be outside of 3 standard deviations in most situations. You're 10 standard deviations away. If we were talking about human height, that would be like having an 11-foot person walking around. You say, nah, it probably can't happen. Well, it could happen. It hasn't happened yet, okay? It's not going to happen. So you can actually test things without actually doing anything by just looking at the numbers when it's binomial in nature. Okay, I've got a coin, and we do coin flips all the time, just for fun, you know, $1 for heads, $1 for, you know, we just play a coin. But I feel like I'm losing most of the time. I feel like I have a semi-Harvey Dent coin, right? It just lands tails way too often, and I always pick heads. Is there a way to know if my coin is fair? Well, I can melt it down, I can, you know, divide it, I can drill it. No, I mean, just like, is there a way to know it's fair just by flipping it? Yeah. You like this. This is real life, this is what we do. Can we go ahead and close that for a minute? Yeah, I don't think I can compete with that. That's really loud. All right, so you're trying to determine, now let's say it, this is a really serious situation. This might be a court of law kind of situation where I want to get it right. So I'm not going to flip the coin 2 times. Aha, they were both tails. It's clearly a weighted coin. But then the next 2 times could have both been heads. Yeah, no, that's not really going to work. What if I said, we have the time, let's do it 1,000 times? I mean, how long would that take you to do it 1,000 times?
Too long.
Well, I guarantee you, unless you're like really uncoordinated, it probably wouldn't take more than an hour. I mean, literally, it wouldn't take more than an hour. There's 3,600 seconds in an hour. If you just did one flip every 3.6 seconds, I think, do you want to do this? No, but let's just say it was really important. You want to get it right. So you flipped a coin 1,000 times, okay? You flipped a coin 1,000 times. If it's a fair coin, P and Q or a half. You're trying to determine if it's a fair coin. So how would I know that? Let's go to the range rule of thumb. What does the range rule of thumb say is the set of reasonable outcomes? Does that make sense to you? So I'll call it again. The range rule of thumb says, well, let's see. My mean or expected value is NP. So 1,000 times a half. I flip a coin 1,000 times. I expect to get 500 tails. Okay? We all agree with that? The variance, and the reason I'm writing them both, because sometimes the textbook will say this, sometimes the textbook will say this. We have to know they're the same thing. This is NPQ, which is 250. And that means my standard deviation, which is the number I'm actually going to use, is the square root of 250. Now you're going to do this on your calculator, so you don't need to tell me what the square root is. All right, so let's calculate. So the range rule of thumb says I should be plus or minus what? Plus or minus what?
270.
So 2 times. Yeah, don't forget that 2. Range rule of thumb says the vast majority of outcomes are within 2 standard deviations. Now let's pull out our calculator. All right? And let's go ahead and put integer values down, because I don't really need decimal numbers of tails. So x is going to be between, the reasonable range of values is going to be between what and what? About. That's not that wide of a range, perhaps. So I'm flipping a fair coin 1,000 times. Is it mathematically possible that a fair coin could be outside this range? Yes, it's just extremely unlikely. So I'm flipping this fair coin to try to determine, well, I'm flipping this coin to try to determine it's a fair coin. And I got 600 tails. What do you think? Now that's way outside the range of what's reasonable. I'd say, no, that's not a fair coin. It's not equally weighted. Here's the problem with doing too few. If I flip a coin 2 times, 1 head, 1 tail is going to happen half the time. 2 tails is going to happen 1/4 of the time. 2 heads is going to happen 1/4 of the time. Those aren't small numbers. But if I flip it 1,000 times, then most of my outcomes should be around 500. I mean, this is a pretty big, plus or minus. So now if I'm getting 600, 700, 800, that is so far out of the range. What if I got 530? Would you question whether it's a fair coin? No, you said it's reasonable. This is what we really do in real life, that you actually can do this way. All right? Now let's do the roll of a die. Okay? I always like using 6s. All right? Roll a fair die. By the way, I have to start off with it being a fair die, Because if it's not a fair die, you can't tell me the probability of success and failure easily. That would, how many have heard the term loaded dice? What does that mean? Does anybody know what that means?
One side's weighted.
Yeah, it's actually not very hard to think. Think about it this way. Imagine I have a die that's made of balsa wood, really, really light wood. But in the center of that die, I have a BB, ball bearing. And as long as it's perfectly in the geometric center of that die will land equally on each side. But what if I move that BB closer to one of the faces? Then that face is going to land down way more often than the other ones. That's how you could physically make a loaded die. Put something in the middle, now move it closer to any one face. So if I put the BB right next to one face, that face is going to land down almost every time, isn't it? So whatever the opposite face is going to land up almost every time. That's what it means to be loaded dice, is that the weight distribution is such that each side is not equally likely. And you wouldn't want to play with those dice. Does that make sense? Because then you have no control over probabilities and outcomes. So assuming it's a fair die, that means that every side is equally likely. So roll a fair die, let's say, let's give a nice number, let's say 150 times. Okay? Let X equal the number of sixes. Oops. That's an S. Sixes. All right? Can you tell me the expected value of X and the variance of X and the range rule of thumb? I want a reasonable set of outcomes. So let's do this on our own for a moment. Oh, wait a minute, but I didn't give you any numbers. Or did I? What three numbers do we always need? N, P, Q. That's all you ever need. What's N? 150. What's P?
1/6.
1/6, because I'm only asking for one outcome. There's six possibilities on that die. And therefore, what's Q? 5/6. If I have those numbers, I don't need anything else. This becomes a very simple problem. I actually got an earful last day because we were spotted multiple times by our mess. And they actually said I'm not legally allowed to even be in the room if you're not wearing a mask. So please put a mask. I don't want you to get in trouble. But that's not a suggestion. That's actually an absolute requirement. Yeah. Okay. The expected value is what? Can you tell me? 25. I'm going to roll a die 150 times and count sixes. I expect to get 25. That doesn't mean I will, but again, every one of us in this room rolled the die 150 times. That was the average number of sixes that we drew. That's an easier way to think about it sometimes. Okay? What is the variance then? And we can leave this as a fraction. We don't want to calculate this yet. We'll calculate it with the range rule of thumb. So as a fraction, what is this?
125/6.
125/6. So the range rule of thumb, oh, and by the way, that's, before I go any further, then I need that guy, don't I? And that's what I'm going to enter into my calculator. It serves no purpose calculating 125/6, rounding it off, then calculating the square root of that and then rounding it off, and then using the rounded off number in my next calculation, because no matter what, your last decimal place is no longer correct. No, just do the whole problem using this. You have a calculator. You don't need to keep track of the things, just enter it into your calculator. So now my range rule of thumb, keep going. I want you to tell me a reasonable range because I'm asking for discrete values. I can't have a decimal number of sixes, agreed? So you're going to go ahead and round off your answers. That just makes more sense when you're reporting it. So let's all do that. So a reasonable range. You know, we could probably open that door again. I think they're done with the garbage collection, if you don't mind. You know, usually they like to do that during exams. You'll have an exam going, all of a sudden it's like banging and thrashing around. Thanks, Dylan. All right, we have a number yet.
Yeah. 16 for the lower end. Or you want this to round, right?
Yeah, let's round it to integer values.
Okay. 16 for the lower end.
So you've got about 16 and, you said 34?
34.
Does everyone agree with that? Because that's the right answer. The range rule of thumb says if I roll the die 150 times, this is a reasonable range of values. Outside of this range, it's not impossible, but the probability is so low that we say it's unlikely. Now, the reason this is important is you cannot account for every possible outcome. That's not realistic. I mean, that'd be like saying I want to account for every possible human height, and that's a pretty big range of values. So what we say is I want to capture the vast majority. And what we're going to start with next day is you can actually give me a percent. If you said, I want to capture 90% of the outcomes, or 95% of the outcomes, I want to capture 99% of the outcomes, we would actually be able to do that. Then if I said, I want you to capture 99% of the outcomes, we're going to exclude 1% of them. But which 1% are we excluding? The most likely or the least likely? We're excluding the least likely. They're not impossible, but at least we want a range of values that covers almost everything. You can never have a range that covers everything because now you have to, that'd be kind of like doing the opinion poll to find out who people want to vote for. We sample a certain number of people, but I don't want any error. Okay, then sample every single person in the United States and ask them who they're going to vote for. Great, except that's not reasonable. Hundreds of millions of people you're going to do a sample. that might take you months and a lot of money. You can't. So what do? You do a sample and you say, I think whatever my outcome is, I've captured probably 99% of all the possible outcomes. That's kind of how we look at this. It's not realistic to say I'm going to have all of them. I want to measure the salt in ocean water. So I will take all of the ocean water on planet Earth and then, put it in the lab and measure the salt. Or maybe I'll go out to the ocean and take a sample, Because all of the ocean water is probably not practical, is it? I don't think I can get it in my lab. I have a really big lab, but it's not that big. Okay, question. Now you're saying, I'm going to roll sixes, but I got to roll a lot of sixes. How many have ever played the game Yahtzee? It's a dice game. Raise your hand if you played Yahtzee. Yahtzee is a dice game. You had 5 dice, and you roll the dice, and then you have outcomes. Your dice, it could be 2s, 3s, 4s, 5s, 6s, full house, 3 of a kind, 4 of a kind. Wait a minute, full house, 3 of a kind, 4 of a kind. Your outcomes sound a lot like what? Poker. Yeah, Yahtzee is basically a game that was invented. It's poker with dice. And kids play it. It's a really easy game to play. And you roll 5 dice, and let's say you got 3 4s and then 2 of something else. So then I put the other 2 dice back in and I roll them to see if I get more 4s. Wait a minute, isn't that what you do with cards? You throw your cards back in. It's exactly the same thing as cards, except you're doing it with dice. And now there's only 6 outcomes. There's a lot more outcomes with cards. Cards is harder because there's so many more outcomes. But dice, there's only 1 through 6. So Yahtzee was this game invented. It was a really nice game to play. So, you've done everything and you've filled up all of your things. And here's the bad thing is, you got a full house, good, but you can't get another one. You've got a 3 of a kind, good, you can't get another one. So now there's only one thing left, 5 of a kind. And the only way you're going to win is to get the 5 of a kind. So I'm gonna make it easy on you. I'll say, okay, I'm going to give you a choice. You can either go for the 5 of a kind, or you can be struck by lightning. Which one is more likely in your lifetime? To get the 5 of a kind, or to be struck by lightning? By the way, that's 5 6s in a row. What is the probability of 5 6s in a row? Wouldn't that be 1/6 to the 5th power? What is that? I don't know what it is. Would you say this is very likely? This is not very likely. Now, it depends on what website you go to. I just went to one this morning, because it's one of those calculations. Your probability of getting 5 sixes in a row is this. Your probability of being struck by lightning in your lifetime is this. Your probability of being struck by lightning is almost exactly half the probability of rolling 5 straight sixes. Now, most people, isn't that kind of the line in the sand? We always say, you're more likely to be struck by lightning. Don't we always use that? You know, there's actually a number, and your probability of rolling 5 consecutive sixes is almost exactly half the probability of being struck by lightning. So if being struck by lightning we consider to be about as extreme can get, then rolling 5 consecutive sixes is probably not very likely, is it? See, if I double this number, it's almost exactly this number. Oh my goodness. You never would have thought about it that way. So rolling 5 consecutive sixes is really unlikely, but wait, 5 consecutive tails isn't ridiculous. No, that's only 1 out of 32. This is 1 out of over 7,000. Yikes. Now, one of my favorite questions that I ask, I put this on a test later. You have a stadium full of people, maybe 60,000 people in the stadium. Let's make it easy. You have 60,000 people in the stadium. What is the probability that any individual gets struck by lightning in their lifetime? 1 in 15,300. Okay, I have a stadium of 60,000 people. It's a football game. How many of these people should I expect will be struck by lightning at some point in their lifetime? 4. Good. How'd you get that? You said 60,000 times this, and it's almost exactly 4. Is that one of the craziest, coolest stats you've ever heard of? You take a stadium full of people at a football game. That means, mathematically speaking, you should expect. Now, if it's a big place like, University of Michigan or something where they actually have 100,000 stand in the stands, it's probably more like 7 of these people are going to be struck by lightning in their lifetime. Isn't that great? Because you're either struck by lightning or you're not. It's a binomial experiment, and there's nothing that's going to change the probability. You either are or you're not. It's a binomial experiment with a measured probability. How did they come up with this? Well, they measured all the people that have been struck by lightning and just look at how many people there are. Now, that's kind of a crazy stat. So stay indoors, I guess, right? No. That doesn't mean you're going to die, by the way. That just means being struck by lightning. Are there parts of the country where you're more likely to be struck by lightning? Do we have a lot of lightning storms in San Diego? No. So the probability of you being struck here is not that great. This is any person. So, you're probably okay. It's sort of like, hurricanes and tornadoes and stuff. We're not in that environment that's really a big threat. Okay. So far, so good? So, last thing I want to do, Kobe watch. All right. We looked this up the other day. In Kobe Bryant's career, his probability of success for shooting a free throw was 0.837. We looked this up last week. Oops, sorry. I looked this up last week. Now, since he's not shooting any more free throws, that's obviously a constant. So the question is, if we took any point of his career, we said, let's look at any 1,000 free throws. I'll use 1,000 because it's a nice big number. If Kobe shoots 1,000 free throws, I would like a reasonable range of successes. Does that seem like a ridiculous question, or does that seem like an easy question at this point? So what do we need to calculate? We need to calculate the expected value, the variance, and therefore the standard deviation, and then we can use the range rule of thumb. If his probability of success is 0.837, then what's his probability of failure? 163?
Oh, yeah.
Got to add up to 1, right? All right, so let's calculate. He's shooting 1,000 free throws. That makes it kind of easy. So let's calculate these. Now, his variance is going to be some icky decimal, and that's okay. Now this, I don't have to round this off, I can report that as a decimal. So if you want this to be exactly. Okay. So Kobe's going to shoot 1,000 free throws. What is a reasonable range of successes? So the answer would be 837 plus or minus 2 times the square root of that number right there. And again, let's give integer values because you can't have decimal numbers of successes in this case. Roughly, I got that at one end, and that at the other. Anybody else get that, roughly? So, Kobe's going to shoot 1,000 free throws. It's reasonable to say he's probably going to make between 814 and 860. Now, could he make 900? I mean, he's a pretty good free throw shooter. Sure. But it's a lot less likely to go, wait a minute, but him making 9 out of 10 in a game, he did that kind of stuff all the time. Yeah, but you're not talking about just 10 free throws. You're saying continued success over a really long period of time. Again, I'm flipping a coin. I can get 2 or 3 tails in a row. But if I did the coin several hundred times, I'm not going to get several hundred tails in a row. Oh, so never confuse small with big. This is a reasonable range of values. It would be unreasonable, in other words, for him to make 900 out of 1,000. Not 9 out of 10 is okay. 900 out of 1,000, that's less likely because, again, his probability of success isn't 0.9. It's not. It's too far. But all at the same time, is he going to only make 700? Extremely unlikely he'd miss that many. So this is kind of neat because this calculation is really simple. Yes?
What about like the unknown factor? Like, let's say he gets tired. Obviously, as old as he was, he would get tired.
This is well, we're not saying 1,000 at one time. We're saying that. By the way, that is a great question because are there factors like fatigue that could set in if we did all this once? Oh, absolutely. Well, I'm saying let's take during the, this would be like a season and a half, let's say, any 1,000 free throws in his career. So if you go back to his career from the first day to the last day and you took any sequence of 1,000 free throws, not a free throw here, a free throw there. No, I mean 1,000, maybe his first 1,000, his last. You're going to find that he stayed in this range always, pretty much. Even the highs, he was over here, the lows, he would be here, but he really would always stay in this range because, again, it's still a binomial. He makes it or he misses it. And because we're talking only a few at a time, things like fatigue are much less likely, as you all know that. You know, and Kobe never got tired. We know that. Right, when he tore his Achilles, you guys remember that? He tore his Achilles, couldn't walk, but before he left, he shot his 2 free throws. then he left and missed the next year because he tore his Achilles. Yeah, tough as nails. All right, go ahead and stop.